Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on February 2nd, 2026, just 3 days ago. It introduces a new neural simulator that uses 3D Gaussian splatting to model deformable objects, boosting resimulation accuracy and generalization on real-world robot tasks by 20%. The paper is titled SoMA, a real-to-sim neural simulator for robotic soft body manipulation. And, as we'll see shortly, the results on complex tasks like long horizon cloth folding are particularly impressive. On Hugging Face, you can download the SoMA simulator weights and find usage examples for modeling soft body dynamics through high-fidelity, action-conditioned Gaussian splatting. So, Figure 1 illustrates the overall pipeline. On the left, the process begins with real-world data collection, capturing multi-view RGB video and robot joint states as an arm interacts with a deformable object, like this blue shirt. Then, the middle panel details the core SoMA framework, which uses these inputs to learn an action-conditioned simulator anchored on Gaussian splats. Finally, the results on the right are split into two parts. The top rows show interaction-consistent resimulation of the original task, while the bottom rows demonstrate the model's ability to generalize to unseen manipulations, maintaining high visual fidelity in both cases. Figure 2 breaks down the specific framework mechanics. On the far left, the system takes in raw RGB observations from a mounted camera, along with the robot's joint space actions. In the central and right panels, the method reconstructs the object using hierarchical Gaussian splats. But there is a key twist. Instead of just regressing positions, it models dynamics through forces. This allows robot-induced forces and environmental effects to propagate naturally through the object's clusters. To make this stable, the top section shows a two-stage training strategy, which first learns global motion patterns with large time gaps, then refines fine-grained details frame by frame. Alright, while Figure 2 detailed the training mechanics, Figure 3 now puts the system to the test with a qualitative comparison across three object types: a linear rope, a planar cloth, and a volumetric doll. The left panel, shaded blue, displays resimulation performance on known trajectories. In the second row of each block, SoMA generates stable dynamics that closely track the ground truth above it. Conversely, the baselines in the bottom rows, Fizz Twin and Gauss Sim, suffer from visible artifacts, marked by red boxes, such as tearing in the cloth. The right panel, shaded green, confirms that this robustness holds even for generalization to unseen robot actions. So, while the previous figure showed us the visual quality, Table 1 now provides the hard numbers to back it up. The evaluation is split into two main sections: resimulation on the left, which measures performance on known trajectories, and generalization on the right, which tests unseen actions. In the bottom row, we see that SoMA achieves the best results across all metrics. For instance, it reaches a peak signal-to-noise ratio of nearly 3.5 in resimulation, beating the Fizz Twin and Gauss Sim baselines by a significant margin. This improvement proves that the force-driven approach captures the underlying physics much better than standard methods. Well, having seen the top-line results, Table 3 now breaks down which components actually drive that success through an ablation study. The table compares the full model on the left against restricted variance. A key finding appears in the image-only column, where generalization scores drop to about 29. This confirms that blended supervision is critical for transferable dynamics. Furthermore, the far right column shows that removing multi-resolution training also degrades stability, validating the course-defined strategy. Alright, finally, Table 4 positions SoMA within the broader landscape of simulation techniques. It compares the framework against alternatives like world models and rule-based simulators. A key limitation of existing approaches is visible in the fourth column, where standard neural simulators lack control-aware dynamics, meaning they cannot reliably predict how objects react to specific robot forces. In contrast, the SoMA column on the far right checks every box. By coupling explicit physical states with interaction-based consistency, it uniquely satisfies the requirements for effective real-to-sim applicability. Wrapping up, the key takeaway is that SoMA effectively bridges visual geometry and physical control by treating Gaussian splats as force-driven particles. This approach boosts accuracy by 20%, offering a robust backend for training robots on complex soft-body tasks without manual tuning. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.